Hello, hello, welcome to the course Introduction to Semiconductor Devices by Professor Naresh Kumar Imani of IT Hyderabad. This is week 10 of the course. I'm Mayank Goel. I'm a research scholar in the Department of Electrical Engineering, IIT Bombay. The course is being taught by Professor Naresh Kumar Imani, who is an associate professor in the Department of Electrical Engineering, IIT Hyderabad. The course plan for this week is technology scaling and Moore's law, qualitative understanding of short channel effects, velocity saturation, channel length modulation, drain-induced barrier lowering, differences in IV characteristics of long and short channel MOSFETs, overview of modern FETs, that is FinFETs, Tandem FETs, and nanowire transistors. This live tutorial session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. First, we will do a recap of the lecture. So last week we studied MOSFETs and their characteristics. Now we'll talk about scaling. So MOSFET scaling basically means reducing the size of a MOSFET. So mainly three components of a MOSFET are scaled: the length, the channel width, and the gate dielectric thickness. So you can see if all three of them are scaled, then the overall footprint of a MOSFET reduces, and we can pack more MOSFETs in a given area. So that way we can increase the transistor density. So scaling was first proposed by Dennard et al. In 1974. So the concept is to reduce vertical and lateral dimensions by alpha. That is length to alpha L, W to alpha W, and Tox to some value Tox. Next is to reduce supply and threshold voltage by alpha. That means your VDD becomes alpha VDD and VTH becomes alpha VTH. Next is increase doping concentrations by alpha. That is substrate doping goes to substrate doping by alpha. So alpha can be some value less than alpha can be some value less than 1, such as zero point 0.7. Scaling classical MOSFETs. Lateral and vertical dimensions reduced by 30%. W equals to zero point 0.7, L equals to zero point 0.7, and T equals to zero point 0.7. Supply and threshold voltage is reduced by 30%. VDD is equal to zero point 0.7 and VTH is equal to zero point 0.7. So if we do that, the MOSFET area is given by W by L, which is 0.49. So it reduces by 50%. Gate capacitance is Cg equals to Cox into WL. So if you calculate that, that comes out to be the zero point 0.7. So gate capacitance reduces by 30%. Gate capacitance per unit area increases by 40%. Current is current drain current ID equals to mu Cox per unit area. Cox W by 2L Vgs minus Vt square. If you put all of that, you will get that current also reduces by 30%. Then time delay is given as Cv by I, that also reduces by 30%. Then power dissipation, which is given by Cv square F, that reduces by 50%. So scaling trend from 1970s to early 2000s, you can see how the frequency has increased from zero point 0.1 megahertz to almost 1 gig above gigahertz, whereas power dissipation is almost now 100 watts, so, so which is double. So technology node, that is parameter to capture the smallest distance between MOSFETs. So you can see technology node has gone from 3000 all the way to 5 nanometers. So you can see it started at 250 nanometers, then at a reduction rate of 30%, that is 0.7x. It went to 180, then 130, then 90, then 65, then 45 nanometers in 2000. And from that 32, 22, 14, 10, 7, 5, and then 5 nanometers in 2020. So if you so by this, so the number of by this by this factor, the number of transistors, if we see the trend here, then we can say the number of transistors per unit area double approximately every 2 years. This is called Moore's law. So now we come to limits. So limit of supply voltage scaling. So this is the graph for 180 nanometer NMOS with W equals to 15 micron, length equals to 10 micron, and VDD equals to 1.8 volts and VTH equal to zero point 0.5 volts. So the transfer pressure looks like this. So you can see the difference between on current, which is 1.8 volts, and off current is much higher. So almost six orders, 6 to 7 orders difference is here. So you can see I on by I off is here around 10 per 6, so 6 orders of difference. So now if I reduce my VDD to 1 volts, so what does this mean? That at 0 volts my transistor is off, that is logic 0, and at my VDD volts the transistor is on, so at 1 volt I am saying my transistor is on, that is my logic 1, and my threshold voltage always lies somewhere between VDD and 0. So here the threshold voltage is 0.45 volts. So the difference between threshold voltage and my logic values are called noise margin. So here this is called noise margin low and noise margin high. So if my so for VDD equals to 1 volts and VTH equals to zero point 0.5 volts, so my noise margin low is 0.45 and my noise margin high is 0.55, which are both almost equal and very large values. Now, if I reduce my VDD to zero point 0.6 volts, but my VTH remains at 0.45 volts, then my noise margin high will become zero point 0.2 volts, which is very low, and it will also cause an increase in the drain current. Now, if I reduce VTH, so if I want to reduce my noise margin, increase my noise margin here, I will have to reduce my VTH. And what will happen if I reduce my VTH? My off current, that is the current at 0 volts, will be at a much higher value. So my I on by I off will reduce if I reduce VT. Also, we have something called subthreshold swing, which is between 60 to 90 millivolts per decade. So if I want I on equals to 1 micron and I off equals to 100 pico, then I need a VG change of about zero point 0.3 volts. If if that is not that I don't have that much VG, then I will not have the, my ion by IF will not be that much value. Technology scaling and microprocessors trend. So this is the trend. So you can see there has been an exponential increase in the transistors, while there has been an increase in frequency, but it has become stagnated, and that is due to RC delays in the circuits. And the power has also stagnated to around 100 to 120 volts, typical power of the circuit. The number of logic cores was one till a lot of time. In recent years, it has increased a lot till almost 20 to 100. So you can see here in 2007 and 45 nanometer node, the size of a die was around 100 millimeter square. Size of processor was around 100 millimeter square. Now it has reduced to 7.6 millimeter square for 10 nanometer node. So this increases the transistor density, but it also increases the complexity of the process. But overall, the cost per transistor reduces. So, so you can see here, size taken per transistor has reduced here over the nodes, but the cost per mm square of wafer has increased exponentially. But when you multiply both of them, the cost per transistor has reduced. So how small are scaled MOSFETs? So this is the image of a human red blood cell, and you can see one single SRAM cell of 32 nanometer node, which is corresponds to an area transistor area of 0.171 micron square. That is, you can see it's how much smaller than a compared to one single red blood cell. A single SRAM cell consists of six MOSFETs. So you can see 1981 SRAM cell area was 1700 micron square, and now one SRAM cell area is 0.17 micron square. So that's a change of 10,000 times. So a single contact in the 1980 SRAM cell is much larger than the whole SRAM cell of 2008. No exponential is forever, but forever can be delayed. So Moore's law is an empirical observation that number of transitions in IC doubles approx 2 years. But but this is not. But there are limits to it, which we will study now. So you can see that technology is changing every now. So the early computation devices were electromagnetic. Then came solid state relays. Then came vacuum tubes. Then came the transistors. Then came integrated circuit ICs, which are currently going. So now what is the future of computing? Could it be optical mem- optical memories, optical devices, quantum devices, or DNA computers? Now we come to problems with short channel MOSFET. So a short channel MOSFET is typical length greater than 1 micron and channel length much larger than depletion layer width of source and drain junctions. Uh, and it follows the square law theory, which we studied last class. But in a short channel MOSFET where the typically less than 1 micron, and the channel length is comparable to the depletion layer width of source and drain junctions. And it shows significant deviations from square law theory. So this is long channel MOSFET where the length is much larger compared to the depletion regions. Whereas in short channel MOSFET, the depletion regions and the channel length are comparable. So the square law theory is that in saturation, the ID equals to mu Cox W by 12 VGS minus VT square. So in a long channel MOSFET, that is followed and you get a constant saturation current, nearly and a nearly quadratic equation. Uh, Whereas in short channel, first of all, the even with same W by L, the net current will be much smaller for the same gate voltage, and the increase in current with respect to gate voltage is not quadratic, it's much more linear. And you can also see the saturation current is now much much more non constant. And you can see here the such VD sat is equals to VGS minus VT is also, you can see, quadratic. Here that also is not quadratic anymore. So now we come to velocity saturation. So for a long channel MOSFET, the saturation velocity is around 10 per 7 centimeters per second, equals to mu E, where E is electric field. So the point at which the saturation velocity is called critical electric field, which you can see is around 10 per 4, 10 per 5 volt per centimeters for long channel MOSFETs. So you can see for long channel MOSFETs, if you calculate your at VD sat, you can calculate 1.8 1.8 volts into 10 divided by 10 into 10 power minus 4, which is your channel length. So that comes around 1.8 10 power minus 3, 10 per 3 volt per centimeter, which is much less than critical electric field. So you don't reach velocity saturation in long channel MOSFETs, but in short channel MOSFETs for the given gate voltage, the electric field is 1 into 10 power 5 volt per centimeter, which is much larger than critical electric field. So at the given so you reach, so it's very easy to reach the saturation velocity in short channel MOSFETs, which causes current to become Q inversion by tau, which is Cox VGS minus VT W by tau, which you put there. So it comes out equal to W Cox VGS minus VT into saturation velocity, and hence the increase in current becomes linear with VGS instead of quadratic with VGS. Next we come to channel length modulation. So the channel length modulation is the effective change in channel length due to pinch off of due to pinch off of such of the channel. So for long channel MOSFET, the channel length modulation is not very high, and hence we assume the current to be constant, channel length to be constant. But in short channels, the channel length modulation is very pronounced, and hence we have a high increase in the saturation current, and their saturation saturation current becomes mu Cox W by 12 VGS minus VT whole square into 1 plus lambda VDS, where lambda is your channel length modulation parameter. Then we have mobility degradation. Next we come to short channel effect on VT. So VT we know is given as mu phi b minus QD by Cox plus 2 phi f, and it looks like your depletion region looks like this. So in case of long channel, the depletion region only exists in the channel region, but in the short channel, the depletion region also becomes pronounced near the source and drain in the source and drain regions, and due to this sharing of charges across source, drain, and the channel, the overall depletion region width decreases, and hence your VT reduces. So you can see here that with the VTH is also dependent on your VDS for short channels. So for low VDS, the VT threshold voltage decrease is not that high, but for high VDS, the threshold voltage decrease is much higher. So next we come to narrow channel effect on VT. So if your channel is much narrower, if your channel width is much narrower now, so till now we are talking about channel length. Now we are talking about channel width. If we reduce the channel width, what will happen is the net charges, the net the net the net area will decrease. The net area will decrease, and due to that, the depletion width will have to be increased, and because of that, your VT will increase. So you can see here, if for short channel VT decreases, for narrow channel VT increases. That you can see here, as the width reduces, threshold voltage is increasing for different substrate dopings. Next, we come to something called as drain-induced barrier lowering, also known as DIBBLE. So, for a typical long channel MOSFET, what happens is, as you increase VG, this barrier reduces till there's a current conduction between source and drain, and the Fermi energy also, hence the Fermi energy also reduces. What will happen is, if you for long channel, if you increase your drain voltage, only the Fermi level at the drain will decrease. It won't affect the rest of the device. But for short channel, the effect is transferred to the channel barriers as well. And what will happen is, as you change the Fermi level, as you change the drain voltage, the drain voltage will pull down the channel barrier channel bands also, and it will cause a reduction in the channel barriers due to pulling down of the channel bands by the due to drain Fermi level, and this is called drain induced barrier lowering. And because of that, so if you see, because of that, the threshold voltage reduces because the barrier is lowered without changing the gate voltage. So you can see in long channel, the off current, the subthreshold is not affected by the VDS, but in short channel, the subthreshold gets affected by the subthreshold gets affected by VDS, and it reduces, and there's a reduction in the threshold voltage. So now we come to technology and innovation. So till 2002, we were only doing geometric scaling, which was reduction in horizontal and vertical physics temperature, along with surface voltage scaling to improve performance of planar transistors. From there, we started doing equivalent scaling. That was reduction in horizontal dimensions in conjunction with introduction of new materials and new physical effects, such that such as strained silicon, high K metal gate, self-aligned vias, FinFET transistors. Next, currently that we are doing is 3D scaling, and the future is completely 3D structures as well as heterogeneous integration. So first is strained silicon transistors. So we add an SIN cap layer which creates a tensile channel strain in the channel, or a SIGE in the source and drain to do a compressive strain in the channel. And what they do is they improve the mobility and hence increase the drive currents. Next we do high K high K and metal gate transistors, high K dielectrics and metal gate transistors. So so we want to reduce the gate equivalent oxide thickness, but if we go more and more SiO2 reduction, then tunneling effects will start. So instead of that, we can change it to high Ks and keep the transistor dielectric thickness higher while reducing the effective oxide thickness. And one of the commonest happening is dielectric. And instead of polysilicon gates, we can use metal gates. Next, we come to from planar transistors to tri-gate transistors. So earlier we were doing planar transistors, which was source and drain and source and drain were on the same. The channel was in the same plane as the source and drain with dielectric and the gate on top. Next we come to try gate where your instead of one direction, the so the gate oxide and the gate is covering the channel in three directions, and that increases the gate control effect. And uh, by this technology we can now do this is called finfets, where we can repeat this procedure multiple times in the same substrate, and there and then we take their effective uh, their total net effect as our output, that you can see here, the fins and the gate. Uh, so performance enhancement tri-gate transistors, you can see with planar transistors the off current was 10 per minus 4. With tri-gate the off current became 10 per minus 5. So uh, the while the on current remains same, so it reduces the off current leakage, and it also reduces the gate delay due to much better gate performance. So this is new technology. So new manufacturing processes were invented and enhanced to ensure scaling of FinFET over the last decade. So you can see going from 22 nanometer to 10 nanometer how FinFETs have scaled with their distance between FinFETs has reduced, and the length of the height of the fin has increased. So what is next? Next is contact over gate. So then quad patterning. So which is gate channel effect. Then there's research on 3-5 transistors, that is 3-5 semiconductors. We'll study more about that in next class. 3D stacking. So uh, stacking of transistors one over the other. New synthesis of materials. Then we have a new type of materials that are called 2D materials, which have a much improved gate gate dynamics. Then we have nanowires. Then we have better lithography by using extreme UV patterning. Then we have interconnects, improvement in interconnects. So interconnects means we can make different processes. Then we have integrate different processes. Then we have beyond CMOS technologies. That means using technologies that are not in the that are not traditional typical to CMOS processes. Then we have dense memories. So you can see the 3D stacking process here, where a germanium narrow ribbon transistor is stacked over a silicon FinFET. Now we'll do practice questions. First, consider an N-channel MOSFET where the lateral and vertical dimensions are reduced by 30% and both the supply voltage and threshold voltage are also reduced by 30%. When the transistor is connected to a load capacitor, it is found that the capacitance and delay are reduced by 30%. Then the dynamic power dissipation reduces by dash in percent. 51, 30, 70, 42. The answer to this would be 51%. So dynamic power is given by CV square F, which can also be written as CV square by time delay. So if you calculate that, this becomes 49. So, so the dynamic power is now 49% of before, which is a reduction of 51%. The evolution of various technology nodes over the years is given in the figure below. Comment on the gate capacitances per unit area in technology nodes of 250 nanometer and 90 nanometer. Hint alpha is considered as the scaling factor down each technology node. Cox is equal to Cox 90 equals to 3 alpha Cox 250. Cox 90 equals to 2 alpha Cox 250. Cox 90 equals to Cox 250 by 2 alpha. Cox 90 equals to Cox 250 by 3 alpha. So the answer to this will be Cox 90 equals to Cox 250 by 3 alpha. so so the gap between 250 and 90 is 3 generations, and the Cox becomes Cox by alpha for each generation. So over the 3 generations, it will become Cox by 3 alpha. Given below are two statements regarding the characteristics of a short channel MOSFET. S1. Typically, the channel lengths of a short channel MOSFET are much larger than the depletion widths of the source and drain junctions. The current in a short channel MOSFET shows significant deficiency from the square law theory. Statement 1, S1 is true and S2 is false. Statement S1 is false and S2 is true. Both S1 and S2 are false. Both S1 and S2 are true. The answer to this would be statement S1 is false and S2 is true. Next, in the figure below, VDS versus ID for two MOSFETs are plotted for a gate voltage VGS equals to 1.8 volts. The W by L ratio for both MOSFETs are equal. Identify the type of MOSFET corresponding to the curve in the given in the figure. MOSFET 1 is short channel, MOSFET 2 is short channel, MOSFET 1 is long channel, MOSFET 2 is short channel, MOSFET 1 is short long channel, MOSFET 2 is long channel, MOSFET 1 is short channel, MOSFET 2 is long channel. The answer to this would be MOSFET 1 is long channel, MOSFET 2 is short channel. So you can see here MOSFET 1 is quadratic and follows square law theory, whereas MOSFET 2 is linear and deviates from square law theory. What is the primary mechanism responsible for the reduction in threshold voltage in short channel MOSFETs? Increased body effect, increased gate oxide thickness, drain induced barrier lowering, decreased gate to drain capacitance. The answer would be drain induced barrier lowering. Barrier reduces due to drain bias, which if it reduces the threshold voltage. Which of the following is a direct consequence of the narrow channel effect in MOSFETs? Increased channel mobility due to smaller channel width, decreased subthreshold leakage current with a narrower channel, reduced gate to source capacitance as channel width decreases, increased threshold voltage as channel width decreases. The answer would be increased threshold voltage as channel width decreases. So as channel width decreases, excess depletion charge is significant and hence VTH increases. Strained silicon is used to improve MOSFET performance. How does it enhance device characteristics, particularly in terms of carrier mobility? Reduces threshold voltage by decreasing mobility degradation, increases current drive by enhancing carrier mobility, reduces power consumption by lowering gate capacitance, increases gate capacitance to offset mobility degradation. The answer would be increases current drive by enhancing carrier mobility. The use of high-k dielectrics in MOS transistors is motivated by the need to reduce gate leakage while maintaining high capacitance. Which of the following is a consequence of using a high-k dielectric in place of SiO2 in terms of band diagram? The band diagram of high-k material is larger than that of SiO2. The equivalent oxide thickness decreases while maintaining the same capacitance. The effective electric field across the gate is higher. The conduction band of the high-k material lies lower than that of SiO2. So the answer would be the effective oxide thickness decreases while maintaining the same capacitance. This we have already studied in the MOS capacitor lectures. Choose the correct option from the following statements regarding the FinFET technology. FinFET offers better electrostatic control over the gate than planar MOSFETs. For a similar operating voltage, planar MOSFETs offer much lower delays than FinFETs. Both A and B are true. A is true and B is false. A is false and B is true. Neither A is true nor B is true. The answer is A is true and B is false. So FinFETs are much better gate control than planar MOSFETs, and they are also and FinFETs also have much lower delays than planar MOSFETs. So B is false. According to the graph on performance enhancements in tri-gate transistors, what happens to transistor gate delay as channel current increases? It increases, it decreases, it remains constant, it oscillates. The answer would be it decreases as delay is proportional to CV by I. So as I will increase, the delay will decrease. These are all the questions I had for today. Thank you.